Okay. We had finished up talking about follow-up tests. And so what we've got with these one-way designs, right? So we've got a factor with 2 or more levels. Generally, if we're running an ANOVA model, it's going to have 3 or more. Otherwise, we'd just be running t-tests, right? When we've got 3 or more levels, we find we get our omnibus effect, and our omnibus effect just says that one of these means is different than at least one other of these means, right? Our task is then to go through and try and figure out where that's at. Now, the problem is that we've got compounding error rates, right? And so depending on the number or the level of factors we have in our one-way design, we could have a lot of possible pairwise comparisons. And if we think about all possible tests, that starts to get really big in terms of the number of tests that we could have, right? So what we want to do is set up an approach that starts to manage that family-wise error, so that our error rate, or the probability of committing at least one type 1 error across 5 or 6 different tests is something manageable and not something that's through the roof, okay? Talking about general recommendations, always, particularly as your designs start to get complicated, want to have some sort of idea about what I'm looking for, what I'm expecting to happen to start to guide some of these follow-up tests. Talked about a priori and post hoc. Best plan is always to have some a priori tests, right? Things that you, before you even run your analyses, before you even run your study, you're expecting some things to turn out. These are going to be your primary hypotheses, right? This is you calling your shots on the front end, and the way we run our science, there's some benefits to doing things that way. Now, we talked about planned comparisons as setting up from a classical standpoint, basically just running a t-test, right? Functionally, it's the same thing as the t-test. We're just calculating it a little bit different, capitalizing on the strengths of our design. So the classic approach to running pairwise contrast, looking at group 1 versus group 2 in an ANOVA design with relatively equal cells, relatively equal variances, right? So you've got the same number of people in your different groups. Your variances, you haven't violated homogeneity of variance. You're looking pretty good. You've done a nice job. You've set up a nice experiment, a nice ANOVA model. And so what we're going to do is we're going to reward you for that. And so what we're going to do is we're going to take the difference between mean 1 and mean 2. But then for our standard error, we're going to take our mean squared error from our ANOVA table, right? Remember that your mean squared error is just kind of your average error across all your individual cells, right? And mean squared means what in ANOVA, or in regular talk? What does a mean squared mean? What is that code for? Been a couple weeks. Anybody remember? What is it, Sam?
Variance?
It's variance. Mean squared is just a variance estimate. Mean squared is the same thing as variance. They're identical. They're not anything different than one another. So basically, we're taking the average. Think about your mean squared error as your average within cell variance, right? And if we haven't violated homogeneity of variance, this is a reasonable estimate for all variance, and it's actually a better estimate and a more stable estimate because it's an estimate that's included more observations than as opposed to less observations, right? The more observations we have, the more stable we would expect our statistics to be, and so pulling our mean squared error term from our ANOVA table is expected to be probably a little bit more stable because it's using all the participants in our design as opposed to just looking at a variance estimate for cell 1, cell 2, cell 3, which is going to by definition have fewer people in it, right? So what we're going to do is we're going to pull our mean squared error, and again, have to emphasize this because this is going to, we get to do this if we haven't violated homogeneity of variance, and we're going to divide, in the classic approach, just divide those by n. N is the number of people in each one of your cells. So again, if you've got equal number of people in each one of your cells, this is easy, right? If we have hugely different cells, then this starts to become problematic, right? So mean squared error over n. This is just the same equation for standard error as in your independent sample t-test, except what are we switching out here, Angela?
For the bottom, you're switching out full.
Yeah.
Or variance.
Yeah. So what's our variance estimate in our usual between sample t-test? Not our standard deviation. What do we? instead of our mean squared error, what variance estimate do we have in there for our independent sample? What's that?
For like hedges?
No, for our test statistic. Does anybody remember? And so this is calculating our standard error, but what's our variance estimate we're using in the calculation of our t-statistic? Do you remember? What kind of variance do we calculate? If we're calculating our independent sample t-test, what type of variance do we need to get to calculate our standard error? Pooled variance, right? All this is the same. This is the exact same formula as your independent sample t-test. We're just substituting your cell size for in here, and then just substituting your pooled variance for your mean squared error. Exact same thing, right? Oftentimes these formulas look different, but if you actually start looking at them, it's the exact same thing. There's nothing different going on here. We're just substituting pooled variance for your mean squared error, and we get to do that because we've run a nice ANOVA design. We've got equal numbers of people in each cell. We haven't violated homogeneity of variance, so we're just going to drop that in there. Okay. Your mean squared error is the analog of a pooled variance estimate for all the cells. Okay. Then what we do is we calculate our test statistic and then test that against a critical t-value for if we're generally running a two-tailed test, so alpha divided by 2 with degrees of freedom error from your ANOVA table. Okay, what advantage does that give us? What's your degrees of freedom for your independent sample test? How do we calculate that? Total minus 2, right? So you take the total number of people in group 1, total number of people in group 2, add them up, subtract 2. That would normally be your degrees of freedom for your critical value, right? What's going on? What's different here? Is the degrees of freedom from our overall ANOVA, is that going to be bigger or smaller? Bigger, right? Because again, we're capitalizing on the features of the design, and so instead of taking just the 2 groups and subtracting by 2 and having this smaller degrees of freedom, which is we're going to do what, Katie, to our critical value? It's going to make it bigger, right? So our threshold is to claim significance is going to be harder if we were just running an independent sample t-test than if we're using this approach, okay? And so when we're going through and you're starting to try and tease apart these ANOVA designs into simple effects, this is the critical thing. If we run a nice test, right, and we've got relatively equal people in each one of our samples, and we haven't violated homogeneity of variance, we can start to capitalize on aspects of the design if we're taking a classic approach to this and start substituting mean squared error for our pooled variance, right? And we can start testing our pairwise comparisons against a critical value with degrees of freedom pulled from the overall ANOVA table as opposed to the more stringent criteria we would have if we were just running independent sample t-test. And so what ends up happening is the use of this formula ends up with a more powerful test of your paired sample of your independent paired sample tests. Okay. Now, if we have cells with a design with unequal cells or unequal variances, now all of a sudden we've started. We're not. It's cheating to capitalize on the design because we aren't playing by the rules of the design, right? And in this case, if you have unequal cells or you have evidence that you may have violated homogeneity of variance, then probably what your best bet is, this is going to not be conservative enough, right? This is going to be too lenient. What you would then do is then start teasing apart in an SPSS, just say, all right, well, I want to look at, I've got an omnibus effect in my ANOVA, and so what I'm going to do is I'm going to say I want to test groups 1 and group 3 and just run an independent sample t-test for that, and then make your conclusions based on from there, okay? And again, independent sample t-test, defensible approach. Again, if you only have a couple of comparisons, just run it through here. Again, from a classic standpoint, the idea is if you're calling your shots, if you've got a small set of important comparisons that you've planned and predicted before you even ran the study, convention says that we can run those at per comparison error rates. Now, if you want to be conservative, make sure that you make the decision to be conservative before you run the test, and not find that everything's p less than 0.001, and then you decide to correct for things because you know it's not going to make a difference, right? But if you have, say, 7 different hypotheses, you should probably go through and make some correction there. You can't just predict that everything's different than everything else and run forward with that, okay? So that's if we just want to do pairwise comparisons. But we then jumped into this idea of linear contrast. And the idea of the linear contrast, what can we do with a linear contrast that we can't do with just a pairwise test? Stephanie?
I'm sorry, I was trying to understand something earlier. What was the question?
So we just talked about how to run, basically, in ANOVA, just like a t-test, right? An independent sample t-test. What's different about a linear contrast? What can we do? What does a linear contrast give us the opportunity to do that we can't do with just a pairwise test?
It allows us to test the difference between, so like if we have 3 different opinions, we'd be able to test the difference between group 3 with the average of the other.
Perfect, right? We can set up any number of comparisons, comparing combinations of groups with others. This is really cool, and particularly if we have ideas about these 2 groups should be relatively similar to this group, right? So what I want to do is look at, is the combination of these 2 groups different than this other group over here? Or are these 2 groups different from these 2 groups, and we're going to exclude this 5th group, right? Sky's the limit in terms of the types of things that you can go through. Now, people are often, show of hands, who's intimidated by linear contrasts? Okay, that makes some sense, right? But once we get the hang of it, it's actually pretty easy and straightforward, because at the end of the day, it just reduces down to a t-test. Because we're still running a pairwise test, we're just taking combinations of different groups. And so our linear contrast is just a linear combination of means. And what we need to do is we need to set some weights, right? Linear contrast is specified when our linear combination, when our weights, if we sum up all our weights are going to be equal to 0, okay? So if I have 3 means and I say, and I set my weights equal to 1, -1, and 0, I sum these up, it equals 0, and I have a linear contrast. Morgan, what am I testing here with this linear contrast?
The differences between mean?
What's that?
The differences between each mean?
Is it the differences between each mean? Or which means am I comparing with this set of weights?
It would be x1 and x2.
Perfect. All we've done is we just run a test here looking at the difference between x1 and x2, right, with this set of weights. Difference between the group 1 and group 2. What about here, Rajiv? We've got weights of 1/2, 1/2, and -1. We sum those up, we get 0. We've got a linear contrast. What are we comparing with this contrast here?
We are comparing the group 1 and 2 against group 3.
Perfect. And based on the way I've set these weights up, which would you expect, am I expecting to be bigger than the other?
So the 3 would be bigger than the group 1 and group 2, right?
Well, so if I've set this weight and this weight and this weight, right? So I'm taking basically the average of group 1 and 2 and subtracting the mean of group 3, and if I want things, my contrast to sort of direction of that to, it's arbitrary, it doesn't matter, right? So which one of these means am I expecting to be larger if this is how I've set up the
Group 1 and group 2.
Right, I'm expecting group 1 and group 2 to be bigger, right? Because if group 1 and group 2, the combination of group 1 and 2 are bigger, and then I have a negative weight to group 3, that's going to mean we're going to take the average of group 1 and 2, we're going to subtract group 3, and then if things work out the way I expect, I'm going to have positive contrast. That means group 1 and 2 are larger than group 3. If it's not, though, right, I could end up with a negative, right, which means that group 3 is actually bigger than group 1 or 2, which would be important to take a look at and make sure that we're accounting for that. So setting up our contrast. So how do we set up our coefficients? What we're going to do first identify which treatments we want to take a look at, which means are going to be included in the contrast. Then we want to assign weights as a reciprocal of the number of treatments in a set. So if I'm comparing, if I've got 5 levels to my one-way ANOVA, and I want to compare groups 1 and 2 against 3, 4, and 5, I'm going to have 1/2 and 1/2. So I've got 2 here, 3 here. My groups are going to be 1/2, or my weights are going to be 1/2 for this group and 1/3 for this group, right? And then what we do is we assign one of those groups, one of those weights to a set of weights to be negative. In general, we're going to assign the weights that, for the group that we expect to be smaller than the other one as negative. Functionally, it doesn't matter. It just helps us with interpretation, right? So again, we've got 5 means, want to contrast 1 and 2 against 3, 4, and 5. Here we go. Our weights, 2 of these, 1/2, 3 of these, 1/3. We expect these to be smaller than that, set those negative. We add up 1/2, 1/2, 1/3, 1/3, 1/3. We get a sum equal to 0. We've got a linear contrast here. And what this is going to do is it's going to compare the average of groups 1 and 2 against the average of groups 3, 4, and 5. If our linear contrasts, or if our coefficients sum to 2, what we have is a standard set. This is going to start to be important. The actual values you assign to these weights can be whatever you want. As long as it sums to 0, you've got a linear contrast. Tricky thing is, if you go through and you set a standard set, what's nice is then the value of your contrast is then a literal representation of the mean difference in the units that you're actually working with in terms of this group versus that group. And we'll talk about and show you some of the benefits and drawbacks of this as we go through examples. So again, if you can, would recommend setting your values so they set up a standard set, just because it's going to make your life easier moving forward. So what we can then do, set up the value of our contrast. And if we set up a standard set, this is literally the mean difference in units that we're working with between this set of groups and that set of groups. And what we can do is then we can set a sum of squares for this contrast. This is just going to be the number of individuals per cell, and if we've got a completely balanced design, n is the same number for all different cells. So you take that multiplied by the square of our contrast that we've calculated here, and we're going to take that over the sum of our squared weights. Okay? If we've got unequal cell sizes, even if they're off by even 1, we switch up our the formula for our sum of squares contrast a little bit. It's just basically a mathematical derivation of that. It makes it easier if we've got the same number of people in each cell. But this isn't too hard. We just take this as the square of the value of our contrast over the sum of each one of our squared weights over the number of people in that sample. Okay? So if we've got 3 means, 10 people in each one of these groups, we want to compare the average of groups 1 and 2 with group 3. So we're going to set our weights to 1/2, 1/2, and -1. Alex, which one of these groups are we expecting to be smaller than the other? To be bigger or smaller than 3?
Oh, did you say small?
Mm-hmm. Which one's going to be bigger than the other one? Okay, so we've got 1/2 and 1/2, and the negative, remember the negative is always going to be associated with the group that we're expecting to be smaller, right? If we're taking a larger number, subtracting a smaller number, it's going to give us a positive number if everything is going as expected. So here, the value of our contrast is going to be 1/2 times 0.5, or 1.5, 1/2 times 2, plus -1 times 3. Value of our contrast, 1.25. Now, do we have a standard set here, Katie? Yeah. Okay. Remember, so linear contrast, if we add all of our weights up, we get 0. So 1/2 plus 1/2 minus 1 is what? 0. Okay. Remember, standard set 2. So we get 1/2 plus 1/2 plus 1 gives us what? 2. So we've got a standard set. And what's nice is if we have a standard set, then we know the value of our contrast is a literal representation of the difference between these two groups, right? So because we have a standard set, we can say that literally what we've got going on is the average of group 1 and group 2 is 1.25 points smaller than the value of group 3. Okay. So, and this is what's nice, is because then we can just plug the value of our contrast in. If we've set up a standard set, we can just take the value of our contrast as sort of the numerator of all our other statistics. Okay. And we'll see how this plays out in a moment. But, so we've got the value of our contrast, right? Yeah.
You said that we do have a standard set?
Yep, we got a standard set here.
Why?
So we've got, if we take, so a standard set is, you have a standard set if the absolute value of each one of your weights is equal to 2. So absolute value would change that to 1. So we've got 1/2, 1/2, and 1 gives us 2. We've got a standard set. No problem. All right. So we've got a sum of squares contrast. This is just going to be the number of people in each group, which is 10 in this example, times the square of the value of our contrast here. Multiply that out over the sum of each one of your squared weights. So we have 1/2 squared plus 1/2 squared plus 1 squared, negative 1 squared. That's sum of squares contrast, and it's 10.42. Because the sum of squares contrast is some part of sum of squares treatment, we can start to set up orthogonal contrast, things like that. Don't worry about that. We're not going to. People get excited about this. It's controversial on whether or not it's sort of that exciting or not. We won't worry about that. But because we're running a 1 degree of freedom test, because at the end of the day, we're just running basically the analog of a t-test, right? So we're taking combination of this group minus the combination of this group. So always comparing 2 means, right? So because we've only got a 1 degree of freedom test, our sum of squares contrast is our mean squares contrast, and so because of that, we can go through and take our sum of squares contrast is equal to our mean squared contrast. So we take our mean squared contrast over our mean squared error, and what's our mean squared error, Angela? What's that? Yeah, it's our error term, right? It's our within it's our within cell variance, right? And so this is representing the variability that we would expect if there's nothing going on in terms of differences between these two, right? Gives us an F ratio, and if we go through and we run this test statistic tested against critical value for F with 1 degree of freedom and then degrees of freedom error, we pull from our ANOVA table. We can run through and test the statistical significance, get a p-value for this here, okay? Also, remember we talked about for an F test with 1 degree of freedom in the numerator, that F is mathematically equivalent if we take the square root of that to a t. And so we can take this F value if we wanted to. We take the square root of that, translate it into a t value. It's interchangeable. It's the same thing, right? This is a nice thing to keep in mind and recognize because it allows you to jump back and forth between things, particularly if someone reports a pairwise test with an F just because they ran what they could have ran an independent sample t-test with an ANOVA design just because they wanted to be special. You can take that F statistic and get it back to see if you want to use that for something. Okay. So again, remember that we typically test fine comparisons at per comparison error rates, but if you've got a bunch of them, you should probably think about running some sort of correction. You reduce the number of contrast. Think to yourself, are all of these things really central? And if they are, maybe start thinking about doing some sort of adjustment to your alpha level to make some corrections there. All right, equivalent tests. This is how SPSS calculates things. You'll see it when we run this. We'll get a t statistic. SPSS is just taking the value of your contrast over the standard error of the contrast. Standard error of the contrast in SPSS is calculated as the mean squared error times the sum of your squared weights over the number of people in each sample. This is exactly, these things are functionally equivalent if you have an equal number of people in each cell. And we'll go through and talk about how those two things are identical, okay? But what's nice is that in SPSS it starts to give us corrected tests for violations of homogeneity, variance, and things like that, which is a nice correction to have if we start to deviate from our perfect case that we've assumed up to this point. Talk about managing our family-wise error, Bonferroni, Dunn-Sidek, both ways to manage and start to correct for possible increase in type 1 error for a set of planned contrasts, okay? What you'll see sometimes is someone's like, oh, you ran 50 different tests, you need to Bonferroni correct for that. That's nonsense. That person doesn't know what they're talking about. That's not what Bonferroni correction is intended to do, because if you do that, you're going to get critical or an alpha level of, like, it's only statistically reliable if you're like p less than 0.0003, right? And then probably what's happened is that you're either only going to detect really big effects or things that are way out of whack and extraordinarily weird, and we're going to continue to perpetuate this inflation of effect sizes in the literature. What we would want to do with our Bonferroni correction, and people get this, so all eyes on me, look at me, all right? Your Bonferroni correction does nothing to your critical value. You're not changing your critical T that you would use. It's changing your alpha level. Like, we're just changing what p-value we're going to identify as statistically significant, right? So if we want to Bonferroni correct for 3 tests, what do? Stephanie?
Multiply 3 times our alpha level, which is 1.5.
Close, not multiply.
Oh.
Divide, right? You're going to be running tests at alpha 0.15. Yep, so we're going to take our alpha level divided by 3, right? And that's going to give whatever that number is, that's the p-value we have to hit in order to claim statistical significance, right? What we don't do, don't try and like find what that is and then find a test statistically. Just use that for your p-value. Same thing for your Dunn-Sidek correction. A little more precise. Your Dunn-Sidek is going to be a little more liberal than your Bonferroni, but it's going to be pretty similar. But if you want to just use it just to be fancy, to use something that's different, I do it sometimes. And technically, it's a more precise estimate and correction. You can go through and do that. But these tests are used for the corrections for a small set of tests, 3, 4 tests, maybe, right? Right. Otherwise, these are going to be far, far, far too stringent. If you're correcting for more tests than that, you want to have a different approach than just Bonferroni correcting the hell out of everything. And you get this from reviewers. Reviewers say, oh, you ran 10 different tests, you should Bonferroni correct for those. No, that's not what this is intended for. We have other things that we can do that with. That's not what these corrections are about. Okay. Confidence intervals and effect sizes. Okay. Confidence intervals for our contrasts, mean 1 minus mean 2, or the value of our contrast if we're using our contrast, plus or minus whatever our T, our alpha level is, times our standard error. Standard error here is going to be 2 times our mean squared error over n. Okay? And again, this works out nicely when we've got nice balanced designs and we haven't violated homogeneity of variance, anything like that. Effect size, also very, very similar. What we've got is we're just going to run a Cohen's D, x1 minus mean of x, group 1 minus mean of group 2 over, or if we're running a contrast, just taking the value of our contrast. If we're doing just straight up pairwise tests, we can just go ahead and calculate this with a pooled standard deviation estimate. This is just our Hedges G, right? That's all that is. Nothing new or exciting here. For our contrast, though, what we need to do is we need to figure out, so we've run a contrast comparing groups 1 and 2 against group 3. And we want to calculate an effect size of this, right? So we've ran it, we found that a contrast is statistically reliable, we want to attach an effect size to it, right? Now, numerator is easy. This is this value of our contrast if we've specified a standard set. But then what's our standardizer? This is always the crux with our effect sizes. What do we choose as the standardizer? Because you've got some options. In this case, your standard deviation of your error estimate here, you could take the square root of your mean squared error. Why does this work, Sam? Why can't I just take the mean squared error and take the square root of that? What's that? Yeah, right. If our mean squared error is just basically the analog of our pooled variance estimate for all the cells in my design, and if I take the square root of a variance estimate, I get a standard deviation, right? Basically, we take the square root of our mean squared error. It's like taking our pooled standard deviation of all the cells of all the groups in our design. But if we haven't violated if we got relatively equal number of people in each cell, and we haven't violated homogeneity of variance, given that we don't have a strong reason to expect that our variance estimate is different across each one of those cells, then this is a perfectly fine estimate, right? No problems. But what happens if I'm worried about homogeneity of variance, right? What if I'm concerned that maybe groups 1 and 2 have a different variance estimate, population variance, than group 3? Then if I'm just taking the average across the whole thing, that seems not reasonable, right? Because the group 1 and 2 is gonna outweigh group 3, we're gonna have some problems there, right? So what we could do is we could take the average, the square root of the average variances of the samples in question, right? So we've got equal cells. What we could do is we could just say, well, we've got 3 groups out of, say we've got 5 levels to our factor, right? But we're only looking at 3, right? We're gonna compare 1 and 2 against 3. So what we could do is we could say, well, I'm worried about violations of homogeneity of variance. So what I'm gonna do is I'm gonna take the average variance of groups 1, 2, and 3. I'm gonna take those variances and then I'm gonna divide them by, I said 10 people in each group. Then divide that by 30, right? And that's gonna give me an average variance, not of all of the cells in my design, but just the ones that I'm gonna use for this contrast, right? And so I've got an average variance specifically for the groups that are gonna be included in this contrast, and then I would take the square root of that and use that as my standardizer, okay? Does this make sense? Because again, the mean squared error for the ANOVA table, that's taking the average variance of everybody in the group, or everybody in the design. But if I'm worried about violations of homogeneity of variance, that might not be optimal. And so if I'm worried about homogeneity of variance, what I might do then is say, okay, these are the groups that that are included in the contrast. I'm gonna take the average variances of those groups, if I've got relatively equal sample sizes, and just use that, take the square root of that as my standardizer, okay? People understand what's going on here? Okay. But what happens if I'm also worried about, I'm not only just worried about homogeneity of variance, I got vastly different numbers of people in each group. Now all of a sudden I can't just take the average, because I would expect the cells that have more people to have a more stable estimate of the variance than the cells with less people. I probably want to weight that estimate based on the number of people in each one of these cells. And so if I'm set up with a situation where I have worried about concerns with homogeneity of variance and different sample sizes, then what I might want to do is take the square root of the pooled variance for the samples in question, okay? Basically, this is just a modification of your pooled variance estimate, right? And all we have to do here is going to be n-1 times my first variance plus n2 minus 1 my second variance plus n3 minus 1 for my third variance, and so on and so forth, over n1 plus n2 plus n3 minus 3. Okay. So basically we're just taking your pooled variance, your pooled formula, and you're just adding other variances in there, right? And so let's say I want to compare groups 1 and 2 against groups 3, right? But my overall ANOVA suggested that I have violations of homogeneity variance, and I don't have equal. I've got twice the people in group 2 than I have in group 3, and then group 1 is a whole lot higher than both of those. This might be what I would use to go through and get a pooled variance estimate for specifically the groups that I'm looking at, and then take the square root of that and use that as my standardizer. Okay, so this is where this gets tricky. You have to take a look at what you've got and then start making decision points. Where do I go? What's going to be the best option moving forward with this stuff. Yeah.
Can you restate how, going back to average variance, can you restate how you calculate that?
Oh, yeah, I mean, that's,
You said divide by 30, so we add.
well, I mean,
if
so
there
you
were
got,
10 in each.
there were 10 in each, right? So you got
Yeah.
variance 1, variance 2. Oops. Over, and then if you've got the same number of people in each, right, you just take that over the total number of people who you have in those groups, right? Because you've got 2 more groups, you've got 4 and 5 out there, so you just take the total number of people in groups 1, 2, and 3. And if you're pretty close, if you've got the same number of people in each one of these, right? If you've got 10 people in each one of these, then you're good to go, right?
Why isn't it 30 times, why don't we divide by how many groups?
Oh,
Divide by how many?
no, you're absolutely right, yes, thank you, because that's gonna be way too small.
Yeah,
Yep.
okay.
Thank you, no, excellent, good for you for saying, hey, that doesn't make any sense, so as not to be confusing. Yeah, you're absolutely right. Okay, and the reason we can do this is that we have equal number of people, or, you know, maybe like a difference between, like, so we got 20, 21, and 20 or something like that, then this is fine, right? And the idea being that if you did have the same number of people in each group, and you ran that through this larger pool, you'd get the same number, right? Okay, thank you, Angela, yes. Questions about sort of our decision points up to this space here? Okay, and then also, if you have some sort of control group, right? If you're testing group, difference of group, the average of groups 1 and 2 against group 3, and you're testing that because group 3 is some sort of reasonable, meaningful control group, then just use the standard deviation of that control group, which is giving you sort of an analog of R classes delta. Okay, so this is where it gets tricky, is that you have to take a look and say, all right, what's going on with my data, right? Have I planned, have I got equal groups? Have I violated homogeneity of variance? If I've got a really nice design, really nice experimental design where I've randomized people, got the same number of people in each cell, don't have violations of homogeneity of variance, then things are working out pretty good. But as soon as I start to accumulate violations, that's when I need to start thinking about, okay, where do I go from here? Questions? All right, and again, if you're just gonna plug your, the value of your contrast up here, need to make sure that you have a standard set, okay? I can go through and run my F-test with, say I want to compare the average of groups 1 and 2 against group 3. I can form a standard set with 1/2, and -1. I can also set my weights to 1, 1, and -2, right? Either one of these weights will still give me a correct statistical test. It's just, this is a standard set, because if we add 1/2 and 1/2 and 1, we get 2. Here, we don't get that, right? We get 4. This will still give us a correct statistical test. Our F-test will be correct if we use these weights. But what ends up happening is the value of our contrast is going to be something that's not a representation of the average difference between the means of our groups. Okay. So in general, this is going to be your best bet, but we'll talk about in one of these examples why you might want to, at least for running your statistical test, run something like this if we're in SPSS. All right. So let's go through and open up. You've got your one-way planned contrast handout I gave you last week. Open that up, and what we've got is a sort of a, with our one-way planned contrast data set, what we've got is a hypothetical example, sort of building off of the scenario that we set up that has been standardized to elicit amusement, right? And we are using this as a standardized stimuli to elicit amusement from individuals. But based on some social psych research, we have reason to believe that maybe people's reactions to this film may have at least be somewhat dependent on racial ethnic background, given evidence that we tend to find people funnier who look like us and respond more, give more of a reaction or something like that. So in this hypothetical example, what we're going to do is we want to test out. So we've got participants who are identifying with 4 different racial ethnic backgrounds. We have people who are identifying as white non-Hispanic, black non-Hispanic, white Hispanic, and Asian, right? And so we've got a small pilot. What we want to do is we want to see if we show people this film, are people reacting to the same levels? Basically what we want to know is whether or not racial ethnic background is a moderator of reactivity to this film, right? And we hope not, right? We would hope that this is a standardized film that would get the same reaction on average out of people regardless of background, but who knows, right? This is an empirical question, something that we might want to take into consideration and not just assume everybody laughs at the same type of stuff, right? So what we've got here, simple pilot study, 6 people in each group. We've got people's racial ethnic background that they reported, and their level was reported amusement on a 0 to 8 scale. Okay, 0, not at all, didn't like that at all. 8, funniest thing I ever saw in my life. Okay. So what we're going to do is take a quick run on our omnibus stuff. So we're going to go down, compare means, one-way ANOVA, put racial ethnic background as our factor, amusement is our dependent. And what we're going to do here, hit options, we go descriptives, homogeneity of variance, and then our Welch's. What's our Welch's? You remember what Welch's is giving us? This is our robust test. If we find that we have violations of homogeneity of variance, we'd go to our Welch's test and take a look to see if we have an omnibus effect here. So we're going to hit continue, and we're going to hit OK. And what we get in our ANOVA design here, we have our different groups. We have 6 people in each group in this small pilot. We have mean values for each group, standard deviations, 95% confidence intervals around the mean there, min, maximum, making sure everything looks good. No one thought it was the funniest thing ever, but some people thought it was pretty funny. Some people didn't think it was so funny. Go down through, take a look at our homogeneity variance. Homogeneity variance doesn't look like we have evidence of that. What might be the only thing that we might want to, why might we take this with a grain of salt? What do you think, Sam? Yeah, it's a statistical test. And any statistical test is going to be dependent on the number of people we have, right? And the Levine's test, or our Levine's test here, are we hoping that that's statistically reliable or not statistically reliable? So, not statistically reliable, right? Because if it is, it would suggest that there is we have evidence of a systematic difference across groups. But if I'm hoping something is not statistically reliable, a good way to make sure that it is only have 6 people in each group, right? So wanting to take that into consideration. But if we go through and we take a look at our standard deviations, they're within the same ballpark-ish, right? Now what we would probably want to do if we wanted to do a real specific examination, we would square each one of those. And if we square those, what's going to happen to the differences between these variances? Are they going to get bigger or smaller? They're going to get bigger, right? Why is that unknown? Yeah, right? So the values that are less than 1 are going to get smaller than the ones that are larger than 1, right? And so we want to take that into consideration. Remember, whenever testing differences in standard deviations, it's difference in the variances. But for the purposes of this example, we'll say, okay, we're going to assume that variability across our individual groups are at least reasonable, right? So if we're thinking about how to go through as start to plan this, we've got equal number of people in each cell. It doesn't look like we have strong evidence of violations of homogeneity or variance. And so we're looking pretty good in terms of moving forward with our analyses. Our omnibus test is statistically reliable, right? We see that here's in our ANOVA table, here's our twin groups. This is our sum of squares for differences across our cells. This is our sum of squares, our average within group variability, our total, and then here's our mean squares. Our mean squares are variance estimates, right? This is the variance of mean differences across groups. This is the average variance within groups, and then we've got our F and our significance test here. Here's our Welch's. If we were to have violated homogeneity and variance, this is what we'd be looking at. It looks like our Welch's test is also statistically reliable. So, Alex, tell me what we gleaned from this omnibus test. What do we conclude based on our statistical analysis at this point? Yeah, we would, but give me an interpretation of this omnibus effect. What is this suggesting? What do you think, Kate?
We would probably want to reject the null hypothesis because it looks like there's a bigger difference between groups and communities.
Exactly, right? We would reject the null hypothesis, and our null hypothesis is that people's reported amusement in response to this film was the same across groups, right? This test would say that it looks like reported amusement across these different populations, at least based on these data, it looks like we have evidence that there's a difference in there somewhere, right? At least one group is reporting some type of difference in terms of their overall amusement than others. That's what's telling us, that's what's going on with this ANOVA, or this omnibus effect. What we don't know is where those differences are coming from, right? And this is where we need to go through and take a look. So based on these data, right, based on this pilot, we would say, oh wow, it looks like there may be people with different backgrounds may have different responses or different intensity responses to this standardized amusement film, but want to go through and maybe know what those are so we can start to take that into account, okay? So what we want to do, so what we're going to say is that we have some a priori hypotheses then, and these aren't real a priori hypotheses, these are just make-believe a priori hypotheses for the purpose of having something to talk about. What we're saying that across these four groups, we've got, if people have their things out, I'll save you some time, I won't need to write this out. We've got our planned contrasts. We're expecting one, that our white non-Hispanic participants are going to be more responsive than our people who are identifying as racial ethnic minorities, okay? So we're expecting our participants who are identifying as white non-Hispanic to have higher amusement scores than the combination of everybody else, right? And this might be because our amusement film is depicting white people, and so we're expecting our white participants to think this is more funny than maybe a combination of everybody else. So that's our first planned contrast. Two, we're expecting our white Hispanic and white non-Hispanic participants to be more responsive than our black participants. And three, expecting our black participants to be less responsive than the combination of Hispanic and Asian participants. Okay, so this is just how we've set this up to set up some weights. So if we're looking at and this is the order in which we've listed out our groups. For hypothesis one, what are our weights going to be? So we're expecting our white non-Hispanic participants to have higher ratings of amusement in response to this film than the combination of all other groups. Okay, so 1, and then what's the rest? Maybe 1/3. Perfect. setting up the difference between our one group, who we think is going to have the highest ratings, and our other group, which we're expecting to be systematically lower than our other, okay? So for our second hypothesis, we're expecting our white Hispanic and white non-Hispanic participants to be more responsive than specifically our black non-Hispanic participants, okay? What are our weights going to be here? Okay, 1/2. What's the next one?
I'm going down.
Yep,
Negative
-1 and 1/2 and 0. Perfect. Okay. And again, this is essential. We're going to set these up in SPSS in just a moment, but it's important to know how you've got your groups coded so that you can assign appropriate codes here, right? And finally, our third contrast. What are our weights going to be for this one? 0. -1. What's that? 1/2 and 1/2. Okay. People see how we set up these weights here to start to contrast our different groups. And then once we've got these weights set up, now all we need to do, well, we've got everything that we need to do at this point, right? We've got all the information that we need. So remember that our sum squared contrast is going to be equal to n times the square of y over the sum of each one of our squared weights, and then our f is going to be our sum of squares contrast over sum of squares error. Okay. So let's start by taking a look at our first hypothesis here. What's the first thing that we need to do in this to test this first hypothesis? What do we need? What do we need first, Morgan?
Number of participants.
What's that?
Number of participants in each group.
Yep, number of participants. And how many participants do we have in each group?
6.
6. Okay, cool. So we've got that down. So n equals 6. What do we need to calculate first here? Calculate our contrast. And so for our first one, contrast is going to be 1 times, what's the mean of our first group? 5 plus -1/3 times what? 4.33 plus -1/3 times 6.17, and then plus -1/3 times 6. Okay. Here we can reduce this down, right? We can take this as 5 minus 1/3 times 4.33 plus 6.17 plus 6.00, right? Just a little bit of math there. What do we get for the value of our contrast? Sam, I see you not punching numbers into a calculator. -1/2, perfect. And this is crucial. Has to be negative, right? And Morgan, why is it important to note that this is a negative value for this contrast?
I want to say directionality, but I don't know if that's.
No, it is directionality. Which group did we expect to be reacting more strongly to this film? Right. And what does this suggest? At least in the absolute direction. than it's not, right? So at the very least, the mean difference from our average from our white participants versus the average of everybody else. The average of everybody else is half a point higher than our white participants, right? So something important to note, already we're off base in terms of our hypotheses, just in terms of, looks like a combination of our white non-Hispanic, black non-Hispanic, and Asian participants, they're reporting about a half a point higher in response to this film than our white participants, and so that should already be registering as something that's important, right? So we got the value of our contrast, and now what we need to do is we need to calculate sum of squares contrast. So sum of squares contrast is just going to be the number of participants in each cell, and how many people got in each cell? 6 times square of our contrast is negative 0.50 squared over the sums of our squared weights. So this is going to be 1 squared plus negative 1/3 squared plus negative 1/3 squared plus negative 1/3 squared. Okay? And if we run this out, value of our contrast, we're going to get 1.12. Okay. This is where allowing digits to be stored in your calculator is going to be good. If we round this out to 1.17, 1.17, it'll start to give us sort of weird numbers. But if we keep these digits in your calculator and just run this out, you should get a value of 1.125. People got that? Rajeev's got it. Angelina, did yours figures turn out? Okay. Hey, too dark in here. Okay. Yeah.
0.25.
Okay.
Rajiv, what are you doing?
Oh,
Because I just rounded, like I calculated the bottom.
Okay. Yeah. Well, I mean, to the greatest extent that you can keep things sort of in your calculator, but well, it depends on, anybody working with reverse Polish notation? Anybody know what that is? Okay, well, I would highly encourage it. But in your, people have silly TIs. If you go through and you sort of just put that whole equation in there and run it all out, this is what you'll get, right? So if you're not actually rounding stuff down, right? So if you just took 6 times the square of negative 0.5 over 1 plus 3 times the square of 1/3 and run that all up, it's going to give you exactly 1.125. Oh, no, this one. People figure out their error? Okay, yeah, that'll do it. So you got 1.5 in the numerator, that's relatively uncontroversial. If you take 3, the reciprocal of 3, and square it, you can get 1.1111 out. You get it? Okay. 3, multiply that, you can get 3 infinity. Plus 1. Okay, got it? All right. So we got that squared away. Now we've got sum of squares of contrast. Now we need to calculate our F statistic, right? So we've got our F is going to be equal to sum of squares contrast is 1.125 over, what do we put here in the denominator? What do we put in the denominator? Sum of squares, excuse me, this is not. Mean squares contrast over mean squared error. Okay? So our mean squared error is what in this case? What do we got, Lauren? What's our mean squared error?
Great question. Oh. What?
Yeah, what is it? What is it, Alex?
Is it 0.908?
That is right.
See, I was heading up.
0.908. Okay. And if we run that out, we get an F statistic of 1.239. Okay. Our critical F for 1 and 20 degrees of freedom. Why am I testing it against 1 and 20 degrees of freedom, Sam? Where do we get that 20 degrees of freedom? Yeah, and where that's certainly the denominator. Where am I pulling 20 from? Right. Well, where am I getting that off of my printout? How do I know it's 20? Alex?
It's the error degrees.
Yep, it's degrees of freedom error, right here, right? So again, we've got a nice balanced design. We haven't violated homogeneity of variance. We can just start pulling values out of our ANOVA table. Okay, so we've got a test statistic of 1.239. We've got we're testing this against a critical F with 1 and 20 degrees of freedom. 1 being because it's just a 1 degree of freedom test. Denominators we're pulling from degrees of freedom error here, which is going to give us a critical F of 4.35. And so what is our conclusion based on our statistical test here? Katie, do we reject or do we fail to reject? Mm-hmm. We would fail to reject, right? And so we would fail to reject the null hypothesis, so we would say that data do not support our first hypothesis that our white participants are going to report higher levels of amusement in response to this film than our participants reporting other racial ethnic backgrounds. Right? In fact, what we've got is we've actually got an effect in the opposite direction, where we have individuals from other more diverse backgrounds reporting greater levels of amusement than our white participants, at least in this study, right? Now, we failed to reject the null hypothesis, but probably what's driving some of that failure to reject the null hypothesis? Small sample, right? And so what might we want to do to follow up to see whether or not we might have basically our mean difference is in the opposite of what we had expected. Now we can't claim a systematic difference because we failed to reject our null here, but what might we want to calculate just to see kind of the magnitude of this difference that we've got here? Effect size, absolutely, right? I'm reading lips from here. So we talked about some different options for standardizing our effect, okay? What might we want to choose as our standardizer for this test?
Would it be the square root of MS variance?
Absolutely, and why can we do that?
Because we have homogeneity of variance and some.
Exactly, perfect. No need to make things harder than they have to be. Again, our mean squared error here is just an average within group variance, right? It's like a pooled within group variance for the whole sample. So this is perfectly fine, right? We haven't violated homogeneity invariance, and so we're okay with this, right? And so here, we're going to calculate the D, and all we need to put up here is our value of our contrast over the square root of 0.908 gives us a value of 0.52. Okay. So, even though we failed to reject the null hypotheses, what we've got is a medium effect in the opposite direction of what we had participated, right? And so if this was my study, or if I was reviewing this, I would say, wow, probably this story doesn't end with, yep, our white non-Hispanic folks aren't any different than our other participants. I'd say, well, we don't have evidence of a reliable difference, but we're also not working with a whole lot of people. And in fact, it actually looks like we've got a medium effect working in the opposite direction of what we would have expected. This is certainly something that we'd want to go through and talk about a little bit more. Okay. What's the last thing that we might want to do, because this is Psych 50, 60, and we always do this. Confidence interval, right? Confidence interval here ends up being pretty straightforward. 95% confidence interval is going to be plus or minus negative 0.50, equals negative 0.50 plus or minus. Here, we need to find what? Our T, right? And so what is our critical T? We need to decide what degrees of freedom we're going to use for our critical T. Probably what are we going to use given everything that we've done to this point? What do you think, Morgan? 20, yeah, right? We're just going to pull our degrees of freedom from our mean squared error, because that's what we've been doing up to this point. So if we take a look and T with 20 degrees of freedom, critical T is going to be 2.086, but we need a standard error estimate, right? Standard error, remember, for our confidence interval is going to be equal to the square root for our mean squared error times the sum of our weights over n. So our standard error here is going to be equal to, oh, whoops, nope, that's not right.
It's 2.95.
What's up? Is it T, is it,
No,
is it not?
Is that equation?
No, that's not, that's,
It's
it's
T
the other
times
one.
the mean squared error over n,
Yeah,
square root of.
yeah. I wrote down the wrong equation there at the top of my box. Square root of 2 times mean squared error over n. There we go. Perfect. All right. So here, standard error, we have 2 times what? 0.908 over 6. Okay. And give us a standard error by my calculation of 0.550. So if we put that here, 0.550 gives us a confidence interval of, I'm going to switch this around, negative 0.65 to 1.65. All right. Okay. People sort of getting what we've got. So what we've got is we've tested our contrast, right? Where we've tested group 1 versus these 3 other groups. We went through, ran a statistical test for that. We then went through, we calculated our effect size, we calculated our confidence interval, right? So working through, and so this was the procedure that we used for this example because of the certain properties of the test and things along those lines allowed us to do some pretty specific things here. Okay. You guys want to do another one of work through another one of these hypotheses? Let's do that. What's that?
So,
Do you remember that? It's a negative value, so it's negative.
Yeah.
So if you take negative 0.5 minus this, it's going to be, yeah, no, you're 1.65. You're right. Negative 1.65. There you go. Perfect. All right. Let's run through one more of these. So let's take a look at our third hypothesis here, right? We're expecting our black non-Hispanic participants to report less amusement in response to this film than our white Hispanic and our Asian participants. Okay, so a value of our contrast is going to equal 0 times 5.00, right? And then we've got minus 1, 4.33, plus 0.5, 6.17, plus 0.5 times 6.0. Okay? People follow me up to this point? And that will give us 1.775. That should work out much more efficiently and easily without repeating decimal places. Everybody got to that point? Okay. So then we need to go sum of squares contrast is going to be 6 times 1.775 squared over 0 squared plus -1 squared plus 0.5 squared plus 0.5 squared. It's going to give us a value of 12.603. Am I on point or did I make an error? I think I'm right.
so what is the value of the sum of square contrast?
Yeah, I got 12.603.
Yep.
And already, relative to what we had previously, what might we be starting to guess about our eventual outcome for this hypothesis versus the last one in terms of statistical significance? Probably a little more promising, right? Value of our contrast, it looks like our white Hispanic and our Asian participants are reporting close to 2-point difference in terms of overall ratings of amusement relative to our black non-Hispanic participants, right? And if we take a look at our sum of squares of our contrast, now sum of squares in and of themselves isn't sort of interpretable, but given that the last one that we calculated was 0.550 and this is 12.6, right? This is looking more promising in terms of finding a reliable difference, right? Okay. Now, all we need to do, calculate our F, so we've got 12.603 over our mean squared error, which is what? 0.908. Gives us an F of 13.879. And recall that our critical value was 4.35. So, Rajiv, what do we conclude based on our hypotheses tests here?
We reject the null hypothesis.
Yeah, we reject the null, right? And conclude that based on these data, it looks like the combination of our white white and Hispanic and our Asian participants are reporting systematically higher levels of amusement than our black non-Hispanic participants. And if we go over, want to calculate an effect size. Once we've got one of these out of the way, this ends up being actually pretty straightforward, huh? Start over. We got D equals the value of our contrast, 1.775, over, what do we use as our standardizer here? Yep, square root of our mean squared error, 0.908. Gives us a value of 1.86. So again, not only do we have a statistically reliable effect, it looks like the combination of our white and Hispanic and Asian participants reporting almost 2 standard deviations, or approaching 2 standard deviations above the mean of our black non-Hispanic participants in terms of average levels of amusement. And then in terms of our 95% confidence interval, do we have to calculate a new standard error? Nope, it's gonna be the same, right? Do we need to calculate a new critical T? Nope, that's gonna be the same, right? So all we do here, we've got, we got 1.775 plus or minus critical T, our standard error here. So we end up with confidence interval 0.63, 2.92. And so our conclusion is that in terms of hypothesis 3, we found that the average, on average, the combination of our white and Hispanic and our Asian participants are reporting an average of 1.78 points higher in terms of self-reported amusement as compared to our black non-Hispanic participants. Range of plausible values for this difference in the population ranges somewhere from about 0.6 points above to 2.9 points above. Right? This effect is associated with an effect size of about 1.8, 1.9 standard deviations. Our combination of our white, Hispanic, and Asian participants are scoring about 1.9 standard deviations above the mean of our black non-Hispanic participants. And so we would identify this as statistically significant. We would reject the null hypothesis and say that at least based on the 2 groups and how reactive they are being to this film. How are people feeling about this? We sort of ran through that example pretty quickly, but people starting to see kind of how we're calculating this out, how these figures are working. Any questions on the hand calculations that we just did? Okay. One thing before we start and turn you loose on a break. So this is what we're doing by hand, right? This is calculating contrast so that you're seeing where these things are coming from. But particularly if we have something that's a little more tricky. In this case, it was beautiful, right? We have equal number of people in each cell. We don't have clear violations of homogeneity of variance, so everything kind of falls kind of nicely into this little paradigm that we have right here. But sometimes that's not going to be the case. Sometimes we're going to want to run contrast where we don't have equal numbers of people, and we do violate homogeneity of variance. It would be nice to be able to run these contrasts with some corrections. We can do that by hand, but that would be tedious. We can just set this up in SPSS. So what we're going to do is go back to our data, and this time we're going to go analyze, compare means, one-way ANOVA, and this time we're going to hit contrasts. Okay? And what it's going to ask us to do is it's going to ask us to enter values for our contrast here. Now what you want to do is make sure that you're very, very clear on there it is. Making sure, and this is where we're setting this up on the third page of this, if you look at your syntax file, what we want to do is we want to make sure that we're setting up each one of these contrasts correctly so that we're not getting answers that we're not expecting. So what we're going to do is we're going to go here and we're going to enter our contrast. So our first weight is going to be 1. Oops. Cancel. And then we've got a problem here. We've got 1/3. We can't enter 1/3 into SPSS. So what we can do is what we're kind of forced to do is go -0.33, and then it won't let us do anything else, right? So we're just going to do that, -0.33. What do we do? It gets stupid here. -0.33, add -0.33, add -0.33, why is it not letting me? Okay, and so this sets up our first contrast. All right, and so then what we do is we would hit next, and we go to our next contrast. So here we got 0.5, add -1, add 0.5, add that, and then 0 for our last one. Okay. And then what we could do is we could go through and hit next, and that would be tedious. Well, just do our last one here. And we enter 0, -1, and then we've got 0.5, and 0.5. Okay. So what we've done is we've just, in SPSS, given SPSS weights. Now you need to make sure that your ordering of your groups are the same as what you're ordering your weights in, otherwise things are all going to be backwards, right? We're going to go ahead and hit continue. We got descriptives, all that stuff is the same. Now I'm going to hit paste, so you can see what I was going to do and then decided not to just because it might be confusing. Once you go through and you've got these contrasts, you just want to, if I wanted to run a different set of contrasts, where I would say, I wanted this to be, say, 1, -0.5, -0.5, and 0, right? I could run that contrast if I wanted to. It ends up being easier than just typing them into your syntax line than fooling around in SPSS because it's a pain. But that's all you would need to do to go through and run that, okay? So what we've done here is in SPSS, set up the same contrast that we just ran by hand. And if we go through and we run that, we see that we get the same output. So we've got our descriptives, our homogeneity of variance, our omnibus tests, and none of that matters because we already know what those outcomes are, right? And what we've got right down here then, this starts to become important, you've got your contrast coefficients. And what you can do, and always want to check this, make sure that the groups that you're contrasting are the groups that you intend to contrast. So here, we're comparing our white non-Hispanic to a combination of our black non-Hispanic, Hispanic, and Asian. Same thing here, we've got our, taking a look at the combination of white non-Hispanic and white Hispanic against our black non-Hispanic, and then sort of our last contrast down here. So everything's panning out. These are the contrasts that we intended to run, verifying that. And then what we have down here, we have our actual tests, right? And what's nice about this is we've got one line that assumes equal variances, the bottom line that doesn't assume, the bottom group that doesn't assume equal variances. Now if we go up and we look at our homogeneity of variance, we're looking pretty good here, right? And so we're probably going to interpret this top group of tests, but we don't have to. If we had violations here, we would probably go down through and look at the not equal variances assumed. And as we go through and we take a look, it looks like we have evidence supporting hypothesis 1 or hypotheses 2 and 3. We don't find evidence for hypothesis 1, but again, noting that this is in the opposite direction of what we would expected, right? Now, you'll notice that the value of our contrasts are a little bit different, and you see an A subscript here says the sum of our contrast coefficients is not 0. Why, Rajiv, is the sum of our contrast coefficients not 0?
Because we're using 0.33.
Exactly, okay. And this might be, because we've got a decimal that doesn't sum up. And so what it's saying is like, hey, you got an error in your weights because it doesn't sum to 0. We don't actually have linear contrast. Now, this is probably close enough. But what could we do to fix this to make it right? Instead of putting in values of 1, negative 1/3, negative 1/3, negative 1/3, what can we change those weights to, Rajiv?
Sum to 1.
So that it sums to 0. We could set this to 3, negative 1, negative 1, negative 1, and that does it for us, right? Now, the value of our contrast isn't going to equal a standard set. And so the value of our contrast isn't a value that we can just pop into the numerator of our effect size. But if we wanted to change this, we just go through and make those whole numbers, and that's going to give us the exact test that we're looking for. So this is nice, this is easy. SPSS is giving us what we're asking for here, right? What if I want to calculate effect sizes? What do I do, Katie? Based on what I've got here, how would I calculate effect sizes for each one of these? Do I have a value of my contrast? Does SPSS give me that? Yeah, right. So for example 4, so for contrast number 2, 1.25 over, what are we using for our standardizer here? 0.908. Oh, okay. This is what happens. People will go through and SPSS will give you all sorts of stuff. If SPSS is giving it to you, use that, right? Don't have to go through and crank out a bunch of hand calculations if you can get it from SPSS already, right? Now, the value of your contrast that SPSS is calculating are a little bit different than ours. And the reason for this, well, because we were actually using 1/3 instead of 0.33, and so that's what's accounting for some of our differences here. But you'll see that we were using just these rounded whole numbers. If you double click on an SPSS, which I'm sure you've done in the past, double click on that table and look at this value, right? That's the number that SPSS is actually calculating, right? And so we're going to go through and we're going to see some differences in the value of our contrast down here, but making sure that we're knowing where those differences are coming from so we can account for those. So calculating our confidence or our effect size is going to be nice. What if we want a confidence interval? Do we have sufficient information in our contrast table here to calculate confidence intervals? Yeah, absolutely, right? We say 95% CI for hypothesis 2, value of our contrast 1.25 plus or minus our test statistic, or our critical value is still going to be 2.086. And what's our standard error going to be?
477.
Perfect. I'll give you a hug. It's right there, right? It's right on the sheet. You don't need to go through. This is, we're going to assume that SPSS has calculated this more accurately than we would by rounding by hand. Your standard error is right there. You just plug that in. 4.77. Or excuse me, 0.477. Right? And is it going to give us our interval estimate there? Okay. And what's nice about this is, let's say we've violated homogeneity of variance, right? And we need to go down through and use these things down here. Now, hand calculating to correct our standard error estimates for violations of this, that would be a nightmare. We could do it, we could make it happen, but it's going to be a pain. But why do it if it's just giving you a correct standard error estimate right there? So even if you're running into a design where you have violated homogeneity of variance and you have unequal sample sizes and things like that, you're like, okay, I'm going to go down here, take a look. I've got my point estimate. I know what my critical value is for 95% confidence interval. Here is my standard error. I can just crank that out. I've got everything I need within this printout. Okay? And this is why it's really, really critical to know what these values are, where they're coming from, what's going on in your equation, because then you need to start lifting stuff out of there. It makes it much easier than grinding out hand calculations. And remember, for these assignments, if I tell you to do it by hand, then I want you to do it by hand. But otherwise, make full use of SPSS however you see fit. Okay. All right. So that was our crash run on calculating contrast. Are people marginally less terrified of contrast than they were before? Okay. Perfect. Let's break and we'll get started with new stuff when you come back. All right, folks. So, for the purposes of having a reasonable amount of time to talk about things that are important and that we should probably talk about in here versus the stuff that you can get, post hoc comparisons, I've got a screencast video that will walk you through different post hoc comparisons, what the different things are. I mean, half the time I feel like those videos do a better job of sort of pacing you through so you can sit down and watch and actually pick some of that stuff up than the nonsense that I put you through here in class. But what I will do is go through and post the link for that screencast video, which will take you through all of the last of these slides along with examples based on the handouts that we've gone to this point. Okay, so go through, take a look at that, and work together as a group. But again, I'm always hesitant to advocate teaching to videos, even though that might be an effective way to do it. So at any point you have questions about any of the stuff we're going through in that screencast, come find me and I'll get you squared away on stuff. Okay? Does that sound good? Perfect. Okay.
So can you also update this slide, like a couple of slides I'm missing in.
Yeah, email me and remind me, and I'll go through and get that posted up. Okay, cool. How are we feeling about up to this point? Feeling all right? Okay, cool. So what we're gonna do is now jump into factorial designs. And if you're strong and feeling okay with the one-way stuff, factorial stuff is gonna be a-okay. Factorial designs, up to this point with our one-way designs, looking at a single categorical variable with continuous outcome. Remember, when you're trying to figure out what analyses do we do, first thing to do in every single case, say, what are my IVs, what are my DVs, what's the level of measurement? If you figure that stuff out, it's gonna push you towards the type of analyses that you should be running, right? If we think about our one-way ANOVAs as an extension of our t-test, right? Allowing us to compare 3 or more groups. T-test is actually a special case of ANOVA, right? We can run t-tests in ANOVA, we just have 2 levels of our IV instead of 3 or more. We get the same thing, we just get an omnibus F with a 1 degree of freedom in the numerator, and what can we do edge align with that F? If we wanted to get a T, take the square root of it, right? Same thing that's gonna happen in these factorial designs. If we've got a factor with only 2 levels, right, and we see a significant omnibus effect for that main effect, what does that tell us? That the 2 groups are different, right? Do we need to do follow-up tests with that? Nope, because all we have to do, if we see that omnibus test is significant, and there's only 2 groups, what do we have to do? We just look at the means, right? There's only one way they can be different if they are, right? But sometimes what we want to do is let's take a look at multiple factors. We want to see how multiple factors start to relate to some sort of outcome, or if we're running nice tight experimental designs, how multiple factors impact an outcome. And here, we could run multiple one-way ANOVAs, right? I've got 2 different factors that I want to look at an outcome. I could run a one-way ANOVA on one factor, a one-way ANOVA on another factor, but again, the problem is we have issues with alpha inflation, right? Those are more tests that we're running. And then the big thing is if we're running multiple one-way tests, we may start to miss important effects that are caused or created by specific combinations of factors, right? If I'm just looking at the impact of condition A and the impact of condition B, I don't get a chance to see if the combination of levels of A and levels of B start to impact my outcome. And so this is where our factorial ANOVA starts to come in. Factorial ANOVA, we're looking at 2 or more factors within the same analyses. Okay? This is more efficient than our one-ways, avoids some complications with type 1 error, and also our factorial designs end up being more powerful than our one-way designs in many situations, and we'll talk about why that is. Also gives us a better sense of generalization, right? What we can start to do is take a look at whether or not differences across groups on a certain factor start to be the same or different once we start putting other factors into the mix, right? So is this something that turns out every single time? Are these differences that we see across these different groups, are they the same every time and under all situations? Or can we start to add in other conditions that starts to change how this pattern of means falls out, okay? And so when we're starting to go through and look at combined effects of multiple factors on a single outcome, we get interactions. Someone tell me what is an interaction effect? Can someone tell me what an give me a conceptual definition of an interaction effect? You'll be able to by the end of the lecture. All right, and what this does is it gives us more flexibility in terms of designing our research. We can start to ask more interesting, more complex types of questions that we can than just asking on whether or not A, B, C, and D are different from one another. So some terminology, a factorial design means that every level of a factor is paired with every other level of subsequent factors, and a full factorial design includes all possible combinations of all independent variables, right? So if we're looking at condition 1, factor 1, factor 2, factor 1 has 3 levels, factor 2 has 2 levels. in a full factorial design, we have all possible combinations of these different cells within the design. We identify and communicate the structure of our factorial designs, given the number and levels of analyzed factors. So if we have a 2x3 factorial ANOVA, it says we've got two factors, right? Factor 1, factor 2, factors A and B. Factor A has 2 levels, factor B has 3 levels. So Lauren, in this 2x3 design, how many individual cells do we have? Absolutely 6, right? So for factor A, we have someone with factor A level 1 crossed with factor B 1, 2, and 3, and then A level 2, factor B 1, 2, and 3. So we have 6 individual, 6 unique populations that we're looking at within this design. So as you can see, these designs can start to get very, very large, very, very quickly. I make fun of Narita students all the time. Narita students come in, I got a 4x6x3x5 design. Like, good luck with that, right? You got a billion different subsamples, right? And things get real nasty real fast, and particularly when we start trying to tease things apart, right? So in your research, make sure you're looking at the factors that you need to be looking at, but also be mindful as your design starts to get very large, it starts to get very complicated, and we start to worry about whether or not we can start to attach adequate interpretations to some of those designs as they get quite large. Okay? So a cell is a subsample that's involving a specific combination of factors. Main effect, this is a difference in means across levels of a given factor collapsing across all other factors. So in this 2x3 factorial design, we're going to have a main effect of factor A and a main effect of factor B. Main effect of factor A is whether or not level 1 and level 2 of factor A differ, collapse across all levels of factor B. Same thing, main effect of factor B is whether or not levels 1, 2, and 3 of factor B are different, collapsing across all levels of factor A. And we'll take a look at a handout in a moment that will sort of give you a better sense of what that looks like. So these are our main effects, and then we have our conditional effects. These are our interaction effects. This is the effect of one factor on our outcome at one level of a different factor, right? So what is the difference in the mean of, difference in level 1 and 2 of factor A at level 1 of B, right? And then what's the difference between group 1 and group 2 on factor A at at level 2 of factor B, and the difference between group 1 and group 2 at level 3 of factor B. These are conditional effects, and we identify these as in the presence of an interaction effect, these as conditional effects because the effect is conditioned on the level of the other variable and factor. So if you ask me, how do members of group 1 and group 2 on factor A differ? Well, I don't know. I have to know what level factor B is before I can tell you that, because the differences that we see across these means is conditioned on factor B. So for our demo that we're going to do here, we sort of taking our heat and humidity example and expanding this out, or excuse me, our temperature example, expanding this out. And so for anybody coming from warmer climates, particularly those in the south, may start to recognize that this is a real thing, in fact, right? So our question before with our one-way design was, what does performance look like at cool room temperature and hot temperatures, right? What we're doing with our factorial design is we're expanding that, so it's not just what is the effective temperature on performance, it's what's the effect of temperature and humidity on test performance. So here, what type of design do we have? Sam, what type of, how do we describe this design?
2x3.
Exactly, we've got a 2x3 factorial design. For factor A is humidity. We've got low humidity and high humidity. So we've got 2 levels of factor A. Factor B is temperature, 3 levels of factor B, 70, 80, 90 degrees. Okay? And so we can see in this 2x3 design, we've got 6 individual cells. These are 6 individual populations that we're looking at. We've got low humidity at 70 degrees, low humidity at 80, low humidity at 90, high humidity at 70, high humidity at 80, and high humidity at 90, okay? And so what we're looking at is whether or not we've got a main effective factor A on outcome. What's the effective humidity on performance, right? Taking a look at our main effective of humidity is going to say, if we take the mean performance across everybody who is testing in low humidity and the mean performance of everybody who's testing in high humidity, do we see systematic differences in terms of, do people perform better at low humidity or better at high humidity? Okay. And this is important to start to wrap your head around this too. Do people see where this main effect is coming from? So we're looking at the effect of humidity collapsing across temperature. So what we're going to do is, so everybody who tested low humidity, we're taking the mean of their scores and testing against everybody who's tested the mean of high humidity. We're just looking at the effect of humidity on outcome. We've also got a main effective factor B. Question here is, what's the effective temperature on performance? Angela, what are the means we're going to be testing at to look at this main effective factor B? Each of the temperatures, right? So everybody who's, we're gonna look at the mean of everybody who tested in 70 degrees, everybody who tested at 80, and everybody who tested on 90. Collapsing across factor A, doesn't matter what humidity, mean here, mean here, mean here. And then we're gonna get an interaction. What are the combined effects of factor A and factor B on outcome? Here, we're looking at the impact of specific combinations of humidity and temperature on performance, right? What we're asking here, we're just saying, does humidity have an impact on performance irrespective of temperature? Here we're asking, does temperature have an impact on performance irrespective of humidity? Here we're saying, does the combination of temperature and humidity start to have an impact on performance? And anybody who's lived in a humid place and transferred up to here, what's the impact of humidity? Would we expect an interaction effect here? Absolutely, probably so, right? Things get hotter and things feel much colder as we start to gather more humidity, right? And so this is a really nice case of where we might expect these two factors to interact, and depending on the combination, may start to impact outcome here. People understand sort of this idea of main effects and interactions here? Okay, so our main effects. Main effects are, we're looking at our marginal means here, okay? Main effect of humidity, our null hypothesis is that our population of individuals completing a task at low humidity is the same thing as the average performance of the population of individuals. Null hypotheses here, we're just saying one's different from the other. We're going to test this with an F, looking at observed variability across temperature means over expected variability if the null is true. Okay. Rajiv, which means are we testing for this main effective humidity?
I think the low humidity.
What's that?
The low humidity.
Okay. So for our main effective humidity, in this table here, where are the means that were being compared?
80.
Uh-huh. And
70.
right? So these are the means. So regardless of what temperature level average at low humidity, average at high humidity. So the variability here between these two groups over total variability if the null were true. We also have main effective temperature. Our null hypothesis is that mean performance of the population of individuals completing at 70 is equal to that of 80, is equal to that of 90. Our alternative hypothesis here is that mean performance differs at least one temperature, right? We don't actually have, we can't put that in statistical notation, it's just one of them is going to be different than the other one, right? And we're going to, where are the means that we're going to be testing to test this main effect of temperature? Along the bottom, right? So this is the variance. The variance in these three means is what's going to go in the numerator of that F statistic over expected variability if the null were true. Where are we seeing expected variability if the null were true? Where's that variability being tested? Sort of a precursor for what we'll talk. We'll hit this in a moment. What do you think, Katie? What do we call variability if that we would expect that the null hypotheses were true? So our error variability, right? Where in these ANOVA designs, where are we seeing error variability at?
Isn't it
Within your cells, right? So again, if temperature and humidity were the only thing that accounted for performance on this task, what would the means, what would everybody in this cell be? Be the same, right? Same thing here, same thing here, same thing here. We'd see no variability. If temperature and humidity were the only things that drove performance, everybody in each one of these cells would have exactly the same score. But we know they're not going to, right? There's going to be some variability. That's what's going to go into the error term here. So these are our main effects. Looking at our margins here. Our interactions, on the other hand, this is going to be variability across individual cells that are going above and beyond what's being accounted for by our overall main effects. So if we're seeing systematic differences across these cells that exceed what we can account for by our main effects, this is going to start to look like an interaction. Okay? From a conceptual standpoint, our interaction, and again, sort of tattoo this into your brain, okay? Conceptually, what our interaction effects are saying is that sort of the nature of our effect of one factor on our outcome depends on some second factor or second factors, right? The impact or the relation of X on Y is dependent or conditioned on some other factor, okay? For a means-based analysis that we're running here, we're saying that the differences that we see across these groups, pattern of differences that we're seeing across these groups is dependent on some other factor that's out there. In the current example, our interaction would say that the impact of humidity on performance is dependent on temperature. Or we could flip that around and say the impact of temperature is dependent on humidity, right? This is always, if someone just says, hey, here's an interaction effect, what does that mean? It means that the effect of one variable on your outcome is dependent on some second variable. Okay. What do we call? What do we also hear interaction effects called? We're talking about like regression stuff. What do you think, Morgan? Moderation, exactly, right? The relation between this predictor and my outcome is dependent on some other predictor, right? So the nature of this relation is dependent on a third factor. Interaction effects or moderation effects, they're the exact same thing. For our mean-based analyses, we tend to talk about this in terms of the nature of the differences, the pattern of means across with outcome is dependent on some other factor. It's all the same thing. So our interaction of humidity and temperature, our null is the effect of humidity on performance is independent of temperature. Our alternative is the effect of humidity is dependent on temperature. Our interaction effects are mathematically symmetrical. We could also flip this around and say the effect of temperature on performance is independent of humidity, and sort of switch those around too. This is a conceptual question, how you want to phrase this. Most of the time we have some base effect that we've established in the literature and want to see whether or not that effect holds true across different levels of some other factor. Okay. Where are we seeing our pattern of means that would suggest an interaction effect, Sam? If it's not, we've already counted, these are main effects. Where's our interaction at? It's going to be in our cells, right? Do we see across our individual cell means, do we see different patterns of effects? So, in this situation, does it look like we have an interaction effect? What do you think, Stephanie?
No.
No, absolutely. Why not?
Because
Okay, so these are the same, right? And what else is going on? So that's one thing. What else? If we take it the other way, what else is going on? We're seeing systematic decreases across temperature, each one, right? Everything's kind of going the same direction. What if we see this? Does this suggest an interaction?
Yes.
Yeah, why is that?
Because the differences are not systematic and high.
Right? We got at low humidity, temperature doesn't matter, but at high levels of humidity, we're getting systematic reductions in performance across increasing temperatures, right? And this is the crux graphically. Anytime you, first thing you do, you get an interaction effect, brakes on everything, stop, throw those means into Excel or whatever graphing software you like to use, and plot these out and take a look and see what's going on. Very, very first thing you should always do is plot out your means, okay? Here is our first example, right? That's this. We're seeing, looks like people are tending to perform better at high levels of or at low levels of humidity than high levels of humidity, but the pattern of means across individual temperature is exactly the same, right? So here, we might have a main effective temperature, or excuse me, main effective temperature, because it looks like as temperatures increase, performance decreases. We might have a main effective humidity, because people tend to perform systematically better at high levels than low levels, but on average, no interaction, because we get the same pattern of means both ways. Same thing here, right? Or excuse me, in contrast here, we've got different things going on here. Key feature of an interaction is non-parallel lines. Here, lines are parallel, no interaction. Here, lines aren't parallel. At low levels of humidity, temperature has no impact on performance, nothing going on. But once we switch over to high humidity, seeing systematic decreases in performance across temperature levels. If we plot these out, we see non-parallel lines. Anytime you see non-parallel lines, that's suggesting an interaction effect. Same thing here, just pulled this out of Howell. No interaction. If we're looking at means of across levels of factor A at levels of B, parallel lines, nothing's going on here, right? Angelina, are we seeing main effective factor A or factor B here for this one? Factor B, right? A looks like everybody's pretty much the same across all levels of factor A, but we are getting levels differences of factor B. Again, no interaction here. I'm seeing a main effect of probably factor A and of factor B probably. Same thing, main effect of factor A, main effect of factor B, but no interaction. The pattern of means is identical across both of these. By contrast, this is what we see in terms of interaction effects. So you nothing going on. Means of A are identical at level 2 of B, but as soon as we switch over level 1 of B, things are increasing. Non-parallel lines, same thing here, same thing here. Okay. People kind of seeing so where our interaction effects are coming up. Same thing, and often in terms of our means-based analyses, we're using bar graphs instead of line graphs, just because it makes more sense intuitively with what we're actually looking at. Alex, are we seeing interaction effect in this graph here? Nope, right? If we take a point at each one of these and draw a line, they're identical. Right? We see this simple effect of factor A, the same effect of difference at 70, at 80, at 90, right? We're seeing high humidity is performing lower than low humidity, but the difference is about the same, the discrepancy is the same at each temperature level, right? Versus here, we're seeing the simple effect of factor A, right? So if we're looking at differences between the high and low humidity, that difference changes whether or not we're talking about 70 degrees, 80 degrees, or 90 degrees. And again, if we plot lines across the top of these bars, we're getting non-parallel lines, right? And so in this case, right, can and should we interpret main effects in the presence of reliable conditional effects? Tricky question. A lot of times you hear people say you can't interpret main effects in the presence of an interaction effect. I say, don't tell me what to do, I'll do what I want, right? But you need to be careful, because if you ask me, what's the impact of temperature on performance, I'd say, I don't know. Is it humid, is it not humid? You gotta tell me, because otherwise it makes a difference, right? I can't tell you what the main effect, what the impact of temperature on performance is unless you tell me if it's humid or not. Because if it's not humid, then temperature doesn't have any impact on performance. But if it is humid, temperature starts to have a big impact on performance, starts to decrease performance. We've got a conditional effect, right? The impact of, the consequences of temperature is conditional on humidity, right? So if you just ask me, I can't tell you, right? And so with these designs, always want to be careful. But in some cases, you might want to, for certain types of things, it may start to be important. You say, let's say we find in a big epidemiological study an interaction of smoking and poverty, okay? And we find that for the impact of smoking, so we're looking at health outcomes, right? And we find that the impact of smoking on health outcomes is dependent on poverty, right? And so we see that for people who are higher SES, that we see less of a discrepancy in health outcomes across smokers and non-smokers than individuals with low SES, okay? Which seems like a plausible way things could pan out, right? But we still have a main effect of smoking. It's just that, and smoking is associated with worse health outcomes. It just seems like poverty exacerbates that, makes it a lot worse, right? So in that case, I would say, well, I would still interpret the main effect, right? Because that's important. Like, yeah, at the end of the day, smoking is not good for you. Smoking reduces health outcomes. It's associated with high levels of heart disease, higher levels of cancer, right? So regardless, so we have an interaction, right? But regardless, smoking is not good for you. It's systematically associated with bad outcomes. However, it looks like those outcomes are even worse. They're exacerbated even more depending on what your SES level is, right? Like if you don't have access to nutrition, healthcare, things like that, things get a lot worse a lot more quickly, right? And so this question, should we interpret interactions or main effects in the presence of interactions? I would say it depends, right? And you get pushback. Some people will freak out at you if you start doing this and tell them to pipe down because you know what you're doing. But it kind of depends on the question, right? And so, but as soon as you see that interaction, you always have to be careful about any type of interpretation you would make about a main effect, because you have to qualify it, right? Because that main effect is dependent, it's not a main effect, it's a conditional effect now, okay? In the presence of an interaction. Does this make some sense? Okay. Other thing to remember is your main effects and your interactions are completely independent of one another. In this situation here, we have a main effect of factor A only, right? Means across level of factor B are identical, but we're seeing a clear difference in terms of differences of factor levels of A, 10 and 20. Same thing here, we've got a main effect of factor A and factor B, right? So we've got a main effect here, a main effect here, but no interaction, right? We're seeing a 20-point drop or a 20-point increase across both of these, 10-point increase across here. Two main effects, no interactions, right? Here, we have an interaction but no main effects, right? Main effect of A, mean value of A collapsing across B are identical. Main factor of B across A is collapsing across A is identical, but we've got a clear differential pattern of cell means in here. This is another nonsense thing you'll hear from people. Well, you can't interpret a main effect, or you can't interpret an interaction if you don't have main effects. Get out of here with that. You know, this is stupid, right? But this is serious. You run into this stuff. You can certainly have an interaction. Your interaction has no impact on your main effects. If you have an exact crossed effect like that, you're not going to get a main effect of factor A or factor B, but you're going to get interaction effects. This is why it's always important to start plotting out your interactions when these come up and start taking a look and seeing what you got. All right, so summary of our effects. Our two-factor ANOVA, 3 separate elements of effects, each with a unique set of hypotheses and significant tests. We've got our main effect of factor A, right? Independent effect of factor A on outcome, main effect of B, and then we've got our interaction of A and B. This is our combined effect of A and B on outcome, and again, this is symmetrical, but conceptually we're saying the influence of one factor on our outcome is dependent on our other factor, right? And so I can't tell you what the impact of factor A is unless I know what level of factor B is that we're talking about. So when we're calculating our factorial, our two-factor ANOVA, conceptually, we've got our total variability. This is all the variability that we have in our pie, okay? We're going to separate that into our between treatment variability and our within treatment variability. What do we call our within treatment variability, Rajiv? What do we call the variability we see within cells? Anybody? Error, it's static, right? It's stuff that because if we had perfectly accounted for everything, everybody within a cell should have the exact same score, right? But they don't, and so we're attributing this to error variance. This is variability in our scores that isn't being accounted for by our measured variables. Our between treatment variability, this is what we're looking for, right? We've got, can take our between treatment variability, section this off into stuff that's attributable to factor A, stuff that's attributable to factor B, and the stuff that's attributable to the interaction. So going through and calculating this. Same ANOVA table as we were before, we've just got a few more cells. We've got a main effect of factor A, main effect of factor B, our interaction effect, our error, and our total. So if we go through and grab this this sheet here, and we're working through, this is our breakdown of hypothetical data from our we're going to calculate here is our sum of squares total, right? And what is sum of squares, Stephanie? What is the sum of squares? If I say, hey, here's the sum of squares, you say thank you for what? Yeah, it's just a measure of variability, right? That's all it is. It's not super interpretable, right? Like, I don't know what to do with it, but I understand that this is a measure of variability. I understand this is a gift for the friendship. Thank you. I don't know what to make of it, but thank you. I understand what it is, right? And so our sum of squares total is just a measure of variability for our entire set of scores. This is the variability. This is the whole piece of the pie that we're working with. Mathematically, what our sum of squares total is the sum of the squared deviations of every individual score from the grand mean. Okay. So if you take a look at your sheet, you'll see your the grand mean of all scores is 4, right? Your sum of squares total would be every single person's score. So you see the grand mean right down there in the lower right-hand corner. Okay. Basically, your sum of squares total is going to be calculated as the squared deviation of every single person in the study's score from 4. So we would take every single score, subtract it from 4, square that deviation, sum it up. That's going to give you your sum of squares total. Okay. This is the total variability that we see in all of the set. Okay. This is our conceptual definition. Computational, we can do this a little bit more quickly. If we take the sum of our squared scores and we subtract it from the square of the grand mean over total number of people in the set, this also gives us our sum of squares total. Okay. Again, and what we're going to do is we're going to split this into between treatments variability and within treatments variability. Degrees of freedom for our sum of squares total is 1 minus the total number of scores. And so if we go through and say our sum of squares total computationally is going to be the sum of our squared scores minus the square of our grand total over n. We can go through and we see some of our squared scores is 840, our grand total is 120, we square that, 30 scores in the sample. Here's our degrees of freedom, we got 30 people in the sample minus 1, gives us a sum of squares of 360, degrees of freedom 29. Okay. People are okay conceptually with what we're identifying as our total variability. So this is our sum of squares total is everybody's deviation from the mean, right? Because if factor A and factor B have no impact on anything, right? Never mind, that's a bad thing. And scratch that, that's confusing, right? This is just looking at all the variability we have in the set, irrespective of where people are, what group people are coming from. Now our sum of squares error, this is going to be the variability within each condition of group, okay? What we're doing here is conceptually, this is, if we take person person K at level I of factor A and level J of factor B. So each person, right? And we're taking each person's individual score from their cell mean, right? So we're taking, so for everybody in this example, we've got people in a low arousal with an easy task, right? Everybody's score in that first group from their cell mean, and calculate that up, and we do the same thing for each one of these individual cells. That's giving us our sum of squares error. We can also calculate this as the sum of our sum of squares per group. So if we take a look at each one of our sum of squares, the sum of squares of 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. If we add up all those sums of squares, that's going to give us our sum of squares error as well. Okay? Or we can get this by subtraction. If we take the sum of squares total minus what we're going to calculate as sum of squares cells, that's going to give us our sum of squares error as well. So a lot of different ways we can go through and get this. But again, our sum of squares error is going to be the sum of the squared deviations of every individual's score from their cell mean. Okay? And again, thinking about conceptually what this means, this makes some sense, right? This is maps onto our understanding of sum of squares error. How much is an individual score different from their cell mean, their group mean? Because everybody, if there was no error, they would be identical, right? But they are, and so if we sum up everybody's sums of squares from each one of these cells, it's going to give us our sum of squares error. This is our variability within cells due to individual differences, error, things along those lines. And our degrees of freedom for sum of squares error is going to be the product of the level of factor A and the level of factor B and the number of participants in the sum minus 1. So we have AB times n minus 1, right? Or we can also calculate this as degrees of freedom total minus degrees of freedom for factor A, degrees of freedom for B, and degrees of freedom for our interaction. So if we want to calculate for this example, sum of squares error is the sum is equal to the sum of squares per group. If we look at the sum of squares per group on a sheet, you've got 18, 28, 26, 8, 20, and 20. Add those up. Our sum of squares error is the levels of factor A, levels of factor B, times the cell size minus 1. We've got 2 levels of factor A, 3 levels of factor B. We've got 5 people in each cell. 5 minus 1 gives us, within treatments, sum of squares of 120 with 24 degrees of freedom. People comfortable with this idea of within sum of squares within treatments? This is probably one of the most important figures that we're going to get out of this ANOVA table because it's our metric of error. This is like our pooled error variance across all cells. Okay. Then we got our sum of squares for factor A. This is our variability across levels of factor A. Okay. We're going to calculate this with a balanced design with n times b, where n is the cell size, b is the number of levels of factor b, and then we're gonna take that multiplied by the sum of the square deviation scores of the mean of each level of factor A minus the grand mean. Okay. So on your sheet, if we see, let's say for, if we're looking at easy versus hard, what this is gonna be is we're gonna take the deviation of the mean for everybody who is in the easy group, which is gonna be 6, and then minus the grand mean, minus 4, square that, plus 2, minus 4, square that, right? This is the variability of the mean of each level A of the factor A from the grand mean multiplied by the number of people per cell times the number of factor B. We can also get this calculation shortcut. We can take the square of our row total, or the number of people in each row, minus the grand total over n. Okay, so if you see total of total score for group, for the row is 90. Total for the row is 30. Sort of square those sums over the number of people, multiply that out, ends up being a shortcut for running this. And our degrees of freedom for factor A is going to be levels of factor A minus 1. So here, again, our computational formula is going to be for factor A. So we got factor A is task, or arousal. Factor A is arousal, I guess, here. So we've got our column total. Oops, and I should flip that around because it's confusing. Candice, can you send me an email? Tell me for this slide I need to switch around row and columns. Okay. So here we see we've got 90 squared over 15. Yeah, I'm nuts. Oh, no, I got it right. Never mind. Okay. Sorry about that. So we've got, for sum of squares A, so this is easy versus hard, right? So we've got our row total is 90 over 15 people. 30 squares was our second row for a hard is 30 over 15 minus our grand total is 120 over 30 people total. Okay, people seeing where these numbers are coming from? Okay, and degrees of freedom A minus 1, so we've got 2 levels of factor A minus 1, and we've got that in, so we've got 120 and 1 degree of freedom there. Factor B is the same thing. It's now we're just using columns instead, at least in this here. So we're going to go through and take the total of column 1, which is going to be this is where I've gotten things screwed up. So I've got my 3 columns as all being the same in this example, and I've apparently got an interaction effect here. So this would, on your sheet, this would be 90, 90, and 90 because our columns are all the same. Here on this example, I've got something different. I've got 20, 50, and 50. What's that? Did I fix it on yours? Oh, okay, cool. Good work for you. I fixed it on yours. I have an old one here, so I guess I screwed this up before and then fixed it, but then didn't grab the right one. So, okay, perfect. We're all good in the hood, I guess. So we got 20, 50, 50. Going through calculating that here. So we got 60 and 2. Okay. And then finally what we're going to do is we're going to calculate what ends up being a computational thing here is our sum of squares cells. This is going to be a metric of the variability across all of our cell means, okay? In SPS, you don't see this sum of squares included in your classic factorial ANOVA tables, but in SPSS, it's going to be listed under your corrected model. Okay, and we'll take a look at that once we get into SPSS stuff. Primarily computational, but kind of like a sum of squares between that we calculated in our previous one-way. Our sum of squares cells is going to contain various systematic variability due to factor A, factor B, and the interaction. And so our formal table, it's not something that's terribly useful because it's just kind of all the systematic differences that's attributable to our factors, not split up across our different individual effects. It's just kind of an amalgamation of this is stuff that we've accounted for, right? And so what we're going to get this, we can calculate our sum of square cells as our number of individuals in each one of our cells times the mean of each one of our individual groups minus the grand mean, right? So we're going to take factor level 1 of factor A, level 2 of factor B, the mean of that group minus the grand mean, level 2 of factor A, level 1 of factor B, that group minus the grand mean. Each one of our cell means minus the grand mean, summing those square deviations up, or we can get the sum of squares cells by subtraction by taking sum of squares total minus sum of squares error will give us sum of squares cell. So again, here, sum of squares cells is 360 minus 120, okay? Now there's no spot for that in our classic ANOVA table, but we can go through and calculate that up, because what we'll need that for is our sum of squares interaction, okay? Sum of squares A times B is the variability of our combined effects of factor A and B. We need to get this interaction, this sums of squares, through subtraction, and the way we're going to get it is we're going to take those sum of squares cells, right, which is our between groups variability here, and we're going to subtract variability due to factor A, variability due to the main effect of B, and the stuff that we have left over from our sum of squares between, which is corresponding to our sum of squares cells, is going to be what's left over for our interaction. So Morgan, if our sum of squares, our variability, our between treatments variability is almost completely determined by main effects of factor A and factor B, what's our interaction effect going to be?
Maybe I don't understand what you're asking.
Okay, so if we've got all of our total between group variability, this is the systematic variability that's attributable to our factors, and almost all of it is accounted for by main effects of factor A and main effect of factor B. What are we going to have for our interaction effect?
You mean in terms of variability?
What's that?
Wait, you mean in terms of variability?
Yeah.
Variability would be 0? It's accounted for by
Close to 0, right? And so we're probably not going to have a non-significant interaction effect, right? Everything that we've accounted for is pretty much accounted for by what level of factor A you're in, what level of factor B you're in, and so the interaction isn't doing a whole lot, right? But in those cases where, remember, sometimes we can get an interaction effect in the absence of a main effect, variability of factor A might be close to 0, variability of factor B not much next to 0. And if this is all between variability we have, then everything's getting dumped into here. Right? So we always get our sum of squares for our interaction by subtraction. Degrees of freedom is going to be the product of degrees of freedom of A and degrees of freedom B. So we go through, we get 240, which is what we got for our sum of squares cells, minus 120, minus 60 is going to give us our degrees of freedom for that. Degrees of freedom for 1, degrees of freedom for factor B's. Multiply that, gives us our degrees of freedom for our interaction. Mean squared, this is easy, right? We just take sum of squares divided by degrees of freedom, gives us our variance for factor A. Sum of squares here divided by the degrees of freedom gives us our variance here. We take this value divided by that value, or excuse me, mean squared, that's what I need to do. So I need to have my mean squared error in there. It's not popping up on this slide in order to get my F statistic, so 120, 24. So this should be 5. Right? Yeah. So I jumped ahead and started throwing in F values here, but we need mean squared error. Mean squared error, same thing, is going to be 120 divided by degrees of freedom 24 is going to give us our mean squared error of 5, right? Which is our represents our average or our combined variability within each one of our cells, right? Is going to be here, and so then to get our F ratio, we would take 120 divided by 5, gives us an F of 240. Candace, can you email me about this and tell me to make sure mean squared error pops up in this slide?
Yeah.
120 divided by 5 gives us our F ratio, our variability that we're seeing across factor B, divided by our expected within, and then same thing for our interaction here. So, 3 statistically reliable effects in this case. We would test these against an F with 1 and 24 degrees of freedom, 2 and 24, and 2 and 24 would be our critical tests for each one of these, right? And we go through and we take a look at that. We see that our test statistic exceeds our critical value across all of these. We'd say we have a significant main effect of task A, so difficulty, task difficulty, irrespective of arousal level, we're seeing differences. We have a significant effect of factor B, arousal, we're seeing systematic differences in arousal collapsing across difficulty, and then an interaction of A and B. Because we have an interaction effect, we would say that the influence of task difficulty and arousal is going to be are interdependent, okay? So we have a conditional effect here, and so what we normally do is we go through and start with this interaction effect and start teasing this apart, okay? Conceptually, and this is always the same. Your conceptual definition of interaction effect never ever changes. It's always the same. It's that we have the effect of arousal on performance is conditioned on task difficulty, or the effect of arousal on performance depends on task difficulty. Or we can flip it around and say the impact of task difficulty is dependent on arousal. However we want to do that, this is a conceptual question, whatever makes the most sense there. Okay. And so if we go through and we take a look at what, at our graph, this is what we get. Angela, how do we know that there's an interaction effect here?
If you were to draw a line, they're not parallel.
Right, we've got a very clear interaction. We've got something very different going on in terms of across levels of arousal for easy tasks. We're seeing performance increase as we go from low arousal to medium arousal to high arousal. This easy task performance is increasing, right? But for a difficult task, we get this inverted U effect where at low levels, performance is low. At medium levels of arousal, we get increased performance, and then at high levels of arousal in a difficult task, performance drops down again. Okay. Okay. Sheila, ignore that. Don't worry about that. We don't have time to screw around with that. In terms of power, okay, thinking about our factorial design, and I mentioned these are often more powerful than our one-way designs. And where we get our additional power for these is our additional factors that are included in this design start to account as covariates for other stuff, okay? Basically what we're doing by including other factors in there, as long as those factors have a relation with outcome, we start to shrink down our error term, okay? So for example, let's say we've got a study looking at emotional arousal, calm to excited, in terms of, in response to fear, amusement, and anger eliciting stimuli, okay? So in our one-way design, we're looking at the impact of emotional, or excuse me, emotion condition on arousal, right? Looking at fear, amusement, and anger, right? And so we show someone a scary movie, a funny movie and an anger-inducing movie, and we were looking at the level at which people are reporting being emotionally aroused by this, right? So this is just a one-way ANOVA, right? We've got 3 levels of factor A, and taking a look at the impact of different emotion primes on levels of arousal. Okay? And so we've got variability due to our emotion condition, and then everything else getting chalked up to error. But let's say in study 2, what we do is we have same question. We want to look at the differences in arousal across fear, amusement, anger, and eliciting stimuli. But this time we factor in participant gender as another factor. Now, I'm not sure if this is going to have a huge effect, but it's probably going to account for some variability in terms of people's reported emotional arousal scores, right? So now, what we have in our effect here, before it was just what movie they were watching. Now, as getting pulled into our variability, we have film condition, we have participants' gender, whether or not they're male or female, and then we have the interaction, right? Whether or not there's a dependency between film condition and biological sex, right? And so what ends up happening here is before, if there is, assuming that there is some systematic association, some relation between participant sex and emotional arousal that they're reporting. Angeline, where did this go in this one-way ANOVA design? Where did that relationship between participant sex and emotional arousal go in this study? Yeah, it just gets thrown into the error variance, right? But as soon as we measure that and put that into our model, it gets taken out of our error term and gets dropped into here. Same thing for the interaction. Takes that now, participant sex in the interaction doesn't have any systematic relation with the way people are rating these films, then we didn't gain a whole lot. But assuming that there is, what we've done is we've taken that error term and we've shrunk it down, right? And what's do we use the same or different error terms when we're running our statistical tests for each one of our effects? What is it, Katie? Is it the same or different? It's the same, right? It's just that our mean squared error is the same in the same denominator of each one of our F ratios. And if we've taken a design where gender or whatever factor it is that we haven't measured gets lumped into that error term, and now we pull that out as systematic error, this gets smaller, right? And if the denominator of our F ratio is getting smaller, what happens to our test statistic, Lauren? I said if our denominator of our error variance is getting smaller because we're accounting for more things, what happens systematically to our ratio? It goes up, right? And so this is where we start to get greater power from our factorial designs, because we're starting to give ourselves the opportunity of accounting for more of the systematic variance in these data than we would with just a one-way design. You'll kind of see where the added power of this is coming from. All right, we'll leave it there and jump into effect sizes for our omnibus designs next time. You guys are champions. Good luck.